All right, this section is a continuation with functions and graphs from chapter 1, talking about elementary functions, graphs, and transformations. Okay, some of the topics in this section will be just to look at some basic elementary functions that are important to have a good understanding of. Also, vertical and horizontal shifts, reflections, stretches, and shrinks, and piecewise defined functions. Okay, the first function that I want us to talk about is what's called the identity function. And basically it just says that a function maps a value onto itself. So like if I put 1 into this, I'm going to get 1 out. If I put 2 in, I get 2 out. If I put -3 in, I get -3 out. So it's not a very interesting function. It is basically the line y equals x, and it's a linear function. So just kind of know some of those general characteristics. And one thing I didn't say is it does have the set of all real numbers as its domain and range. So there's no limitations on domain and range for the identity function. Okay, the square function, same thing, no limitations on the domain. You can plug anything into this. The range, it does start, the range is your y's, so it starts here at 0 and goes up, and so that's why the range is from 0 to infinity. And so anytime you see an x squared function, it's going to be what we call a parabola, which is this U-shaped graph. Okay, the cubic function, its domain and range is all real numbers because it continues to go to the far right and up, and then also down and to the left. Okay, and this is the type graph. It's kind of swirly, like it's always increasing, and this will be your x cubed function. The square root graph, just like we talked about in the first section, the square root graph is a little bit different because we do have some limitations on what can be here for this x. We had said that we can't take the square root of a negative number, so only positive x's can be evaluated here. So because the domain is restricted to being only positive numbers, you see that the graph starts here at 0 and goes to the right, but you don't have any values over here to the left. And so that means the domain is from 0 to infinity, and the range on this one, it starts here on the y's and it goes gradually up. As it goes over, it's going up. Okay, and so that would be, the range would be from 0 to infinity as well. All right, the cubic function, it kind of looks like the cube function, but on its side. And you can take the cube root of negative numbers, so that's why we do pick up a part. It's not just this part here like the square root is, but it's actually also defined for negative numbers. The absolute value graph has a very characteristic graph with the V shape. So that's the main thing. It is defined for all real numbers. Its domain is all real numbers. And the range, unless it's been shifted, the range is simply from 0 to infinity. Okay, so we want to look at some horizontal shifts or transformations of these basic graphs, because if you know those 6 graphs, then you actually by transformations can know infinitely many graphs and what they look like. Okay, so the first thing we want to look at is a vertical shift. So anytime you take just a regular function and add a number to it, you're going to have a vertical shift. If that number is positive, then it's going to shift up, and if the number is negative, it's going to shift down. All right, so like here, if we look at just the basic absolute value graph, let's consider what would happen if this is our basic f of x. And so if I just add any number to it here, if it's positive, it just takes that original graph that went through the origin and slides it up 4 units. So it doesn't change the shape of it, it just slides it. Okay, a shift is just a slide. Okay, so here, if I have the absolute value of x minus 5, I do want you to get in the habit of describing in words what's happening. So here we've got our original function, our original f of x. So this -5 is going to shift it down 5 units. So tell me which direction it's going and how many units it goes. Okay. All right, horizontal shifts occur when it's within the function. So on the vertical shifts, they're outside, but when it's inside the function, that is a horizontal shift. And it's almost like it's opposite what you think, okay? So it's actually going to go left if it's a plus h, and it's going to go right if it's a minus h, okay? So we'll look at some examples. All right, so again, looking back at that absolute value graph, here, instead of the 4 being outside, it's inside the function. So that tells me it's a left-right shift. And since it's plus 4, I always think, like, if I'm looking at the number line, a positive 4 is over here. But when it's inside it's inside the function, it's actually the opposite of that. So instead of going what we would normally think of a plus 4 being on the right, it's actually going to send it to the left. Okay, so you're going to send it to the left 4 units. All right, here you've got x minus 5. So if I've got x minus 5, then that's going to give me a shift, in this case, to the right 5 units. And you can see kind of what the graph looks like. It just takes and slides it over. And this is just summarizing that. Okay, we can have stretches, shrinks, and reflections. So anytime I take the function and I multiply a number to it, then that can have the effect of either a vertical, and these are all vertical. Okay, so a vertical stretch, a vertical shrink, or a reflection. Okay, if the a is greater than 1, then it's actually going to stretch it, excuse me, give it a vertical stretch. If it's between 0 and 1, so like 1/2, 1/3, 0.25, things like that, then it takes and it shrinks it vertically. So it's kind of like it's flattened out. And then if the a is a negative, then it reflects it in the x-axis. Okay, so here, if I've got this 2 out in front, it's going to do a vertical stretch. So it's going to take this function here, and instead of it being as wide as it is, it's actually going to make it more narrow. And it's kind of hard to draw this, but it's a more narrow stretch there. Okay. All right, on this one, if you see, we've got a 0.5. So that 0.5 is going to be a vertical shrink. And sometimes we say by a factor of 0.5. And so instead of it being as wide as where it's at for the standard graph, it's actually going to be flattened out a little bit more. And that's kind of hard to draw, but you'll see on this graph here where it's not quite as much of a V, and it's more flattened. Okay, if we have a negative here in front of it, that negative is going to reflect it in the x-axis. So a couple things here, don't use words like at least not when you're given your answer. Don't use words like flip or it's upside down or things, things like that. Let's try to use mathematical terms like reflected, and tell me where it's reflected. Is it reflected in the x-axis? Is it reflected in the y-axis? So in this case, it is reflected in the x-axis. So where it was opening up, it's now kind of opening down. Okay, so you can see that if you have a negative in front of it, it is going to be a reflection in the x-axis. And I'm not going to spend much time on this, but a negative inside the function actually reflects it in the y-axis. It's not as common to see a y-axis reflection, so we're not going to look at those. Okay. All right, so a couple examples here. we have these two functions. So the first one is x to the third plus absolute value of x. And then we have this other one that looks like this, and you can see kind of what it looks like. So we want to describe the shift that transforms this function to this function. So basically, we want to think about like what happened when we went from here to here. Okay, so when we went from here to here, we replaced the x with an x minus 2. Okay, so it was inside that function, inside the cubic function that we put minus 2. So that tells me it was a horizontal shift. And since it's a minus, it actually is a horizontal shift to the right 2 units. And we can see it the same thing here. Okay, we're not going to have like one piece of it being shifted one direction and another piece the other direction. It should be the same for both here. So the x minus 2, same thing with this. It was just an x, now it's an x minus 2, which is another indication that it moved to the right 2 units. So when we have this one here, we've got the plus 2's in there. So that means it's going to move to the left 2 units. So where we talked about like x squared, x to the third, absolute value of x. That's our kind of basic ones. But we also can apply these transformations to any function that's defined. So like this particular function was defined as a combination of those basic functions. And we still could have a pretty good idea of what type transformation took place with it. Okay, on this last example here, we're working with the x cube, and we want to write and simplify a function that represents shifting the function horizontally to the right 1 and vertically down by 2. Okay, so if I'm going to write this new function g of x, and I want it to take this and shift it to the right 1 unit, well, we know that horizontal shifts occur within the inside of the function. And if I want it to go to the right, then I need this to be a minus 1. If we're going to do a vertical shift down by 2, vertical shifts go on the outside. So I'm going to have a minus 2 on the outside. And that's going to be my expression there. Okay, just a couple questions. Suppose a function f of x is multiplied by 10. How does the resulting graph compare to the original graph? Well, anytime it's multiplied by a number more than 1, that's going to be a vertical stretch by a factor of 10. Here, describe the change when a function is multiplied by negative 0.5. That's going to be a vertical shrink by 0.5 and also a reflection in the x-axis. Okay, so the reflection is due to the negative. The shrink is because this is between 0 and 1. It is something that you see a lot of pricing models are based on different amounts of usage and so forth. So like for instance, when you have your water bill, a lot of times depending on how much you use in a month, like you're going to incur different prices based on the usage of your water. So that's where a piecewise defined function can come into play. And it just tells us that we have a function literally defined in pieces, okay? So one piece would be here, and you only use that piece if my input value is, in this case, less than 0, okay? Then I would use this one if my input value is greater than or equal to 0. So it all depends on the input value as to which piece you use, but you absolutely do not plug it into both, okay? You have to choose which one is the appropriate one to use. Okay, if we look at this one here, okay, I just wanted to see the graph of it a little bit. So we've got two pieces. Think of one piece as y equals x plus 1, okay? So that means if you remember with graphing lines, that means you have a y-intercept of 1. So we're here at the y-axis at 1, and we have a slope in this case also of 1. So I'm going to go up 1 over 1, up 1 over 1. and that's the line that I would graph. Okay, but that line is only true if x is between 0 and 2. Okay, so that means only for this part here, from 0 to 2, is that line what I would use. Okay, I have a closed dot on the 0 because of the equals here, and I have an open dot on the 2 because it's not included. All right, if we look at the second piece, y equals 0.5x. Okay, again, think of it as mx plus b. So it has a y-intercept down here at 0, and it has a slope of 0.5. So that means 0.5 is 1/2. So I'm going to go up 1 and over 2, and that's going to give me the line, if I connect it here and continue it on out, that's the line y equals 0.5x. But that's only true if x is greater than or equal to 2. So that's why we want to leave from 2 on. Okay, so we're going to keep this part, and we're going to do away with this other part here. If we look at this one, I want to graph this. I'm just going to let the origin be here so we get some context for this problem. Hopefully you can draw straighter lines than what I'm drawing. Okay, so we've got two functions. One is, and I'm going to put this in slope-intercept form, so negative 2x plus 4. And then I've got y equals x minus 3. Okay, so for this one, I'm going to go up to 4 for my y-intercept, and that's, I'm going to have a point here, and then I'm going to go down for my slope, negative 2 over 1. So negative 2, 1. Okay, so it looks basically like this. And if you can draw a straight line, that would be helpful. Okay, so we're going to keep that for the part when x is less than negative 1. Okay, so looking at this one here, we've got this line, and if I were to connect all of these dots down through here, that would give me this line. But for this particular function, it's only valid for x less than negative 1. So negative 1 is down here, and that means so I'm going to only keep this part up here, and I am going to put an open circle on it because of the fact this does not have an equal sign under it. This next one has a y-intercept of negative 3. I'm going to go up 1 over 1 because it has a slope of 1. And this is true for x is greater than or equal to negative 1. So that's going to be down here and with a closed dot. We'll connect these. Okay. And so that would be our graph. So we'd have this little piece up here, and we'll have this little piece down here. We would not have these 2 points here. So I do, okay, the last one here, we've got, we'll draw in our graph. Okay, we've got y equals x plus 2 and y equals 2x. So on the first one, we have a y-intercept of 2, and we have a slope of 1. So I'm going to do rise over run and graph this. That's only going to be from negative 1 to 2. Okay, so here's negative 1 and here's 2. So it's going to be this little piece from here to here. Okay, so it's only going to go up to here. And then the next one here, it has a y-intercept of 0, has a slope of 2 over 1. So it's going to, but that's good for x is greater than 2. So that's going to be this part out here. So I'm going to start at 0 and go rise 2, run 1, rise 2, run 1. Then we'll do rise 2 and run 1. And so it looks like it's actually leaving that same point, but with a slightly different slope. It's looking something like that. And so we will close this point in because of the second piece, not because of the first piece. So sometimes the piecewise defined functions actually will connect the pieces, and sometimes they will not connect. Okay, that concludes this section.